Okay, so the big topic of today is to simplify our lives when calculating the derivative. So at this point, we understand the derivative to be this right here. If I've got a function f of x and I want to calculate the slope of the tangent line to some point on the graph of f, I've got to go to all this trouble of taking the limit as h goes to 0 of what we call the difference quotient. And as long as I can do that, the limit exists, then we call that f prime of x as the derivative, and it calculates, we now have this f prime of f function that calculates limits for any point we want from the input. And if it works as a limit, we call it differentiable at that point. And then we had two different interpretations, but really there's just an infinite number of interpretations. But the two of the main ones, well, we already said the slope of the tangent line for some x in the domain of f prime. So if I just input any x to my f prime, I get the slope right out of the box. Then the other thing we can think of it as instantaneous rate of change for any xy pair. And if that xy pair happens to be position and time, distance and time, then we can think of it as velocity. So this calculator that we call f prime of x is very powerful, but this is too much work. So what we're going to learn today is shortcuts. And we're also going to give the derivative lots of different names. So we know that limit as f prime of x. If y is defined of f of x, we can also ask for it by calling it y prime. Now this notation is called differential notation. We'll learn more about it as we see it. So I can take the derivative using differential notation. I just substitute f of x for the y part. And every one of these is asking for the same thing. So you won't be doing anything any different no matter how this is posed to you. You just have to accept that there's many different ways to ask the same questions. It's like a synonym. And the first quick rule we're going to learn that's going to speed things up is how do we work with a constant? Didn't mean to do that. Okay, so this is the constant rule. And if I'm taking the derivative of a constant, it turns out to be very easy. If I've got some constant c, then the derivative of that constant equals 0. So if f of x is a constant function, then f prime of x equals 0. And here's other ways of asking for it. Constant and prime, like I did here, this is taking the derivative of a constant becomes 0. And if we ask for it with differential notation, it equals 0. And if it's y prime, then y equals c. So let's play with some of these with our new little fast rule, so I don't have to go to all this trouble anymore and take the limit, which you would have found if you plugged in a constant for that, it would always render a 0. Okay, so for this first one here, if f of x is equal to 3, then f prime of x equals 0. So, and that makes sense because if you think of f of x equals 3, that's a horizontal line at x equal 3. I'm sorry, at y equal 3. And so if I take any point and look for the tangent, well, the tangent is a horizontal line as well that's coincidental with that line. So that means the slope of that is 0. So for a constant, we get 0. So let's just go through these quickly. Y prime. So if I've got y equals the constant negative 1.4, that's a horizontal line at negative 1.4. And of course, y prime is going to always give me a slope 0. If I ask for d of the constant pi for y dx, and I get 0. Okay, so we're just practicing different ways of asking for the same thing. And so this equals 0. All right, so all constants, the derivative of a constant is 0. So that's good. That's our first fast rule. That's not going to get us very far. This next one is much more useful than you might think at a first glance, but let's go over the rule. It says if I've got some function that is my variable x to a power n, that's any real number, then to get the derivative, all I have to do is simply take that exponent down in front as a product, or the factor, multiply it by the same x variable, and then the new exponent becomes one less than whatever n was originally. So I just slip n down here and take it times x to the n minus 1. And if we want y prime, we do the same thing, or so different notations, same process. So let's try that for this part A. So if f of x is equal to x to the 5th, then f prime of x for that f of x is equal to, well, I take 5 down in front of x, multiply it by x to the 5 minus 1. So of course that's going to be f prime of x equals 5x to the 4th. Okay, so not too bad if it's just this power function. Let's take, if y equals x to the 20 or x to the 25th power, I'm going to speed up a little bit here, then y prime is equal to 25x to the 24th, because that's 25 minus 1. So let's say I've got y defined as t to the -3rd. So then I'm going to ask for it a little differently than they're showing here. Instead of y prime, I'm going to take t to the -3rd prime. So that equals -3 times t, and -3 minus 1 makes that -4. So of course, I could write it, since that's a negative exponent, it would also be correct to write that as -3 over t to the 4. So either one of those would be y prime. And lastly, D. Okay, if I've got derivative request of the value of x to the 5/3, then it equals 5/3 times x to the 5/3 minus 1. Now we have to clean that up a little bit, because remember, 5/3 minus 1, I'm going to scoot up here and just write, kind of remind you that's, I need a common denominator of 3. So I'm going to write my 1 as 3 over 3. And then now I know that that simplifies to 5 minus 3 or 2/3. So my final answer for the derivative would be 5x to the 2/3. Okay, and we've even got more power than that with this, just this rule, because remember that radicals are question.
Yeah, why does the 5/3 in front of the x change to 5? On D.
On part D,
Mm-hmm.
I'm taking the derivative of x to the 5/3. So by this rule up here, I'm going to bring 5/3 down in front of x, because n is my 5/3. So this is n times x, and then this is n minus 1. And so the new exponent is 5/3 minus 1. So up here, I've just rewritten 5/3 minus 3/3. So this is 1. So 5/3 minus 1 makes the fraction 2/3. So that's the new exponent for n minus 1.
But before it was 5/3 x to the 5/3 minus 1. So wouldn't it be 5/3 x to the 2/3?
Oh, yeah, I see what you're saying.
Yeah.
I didn't put the 5/3, I just put 5.
Okay, gotcha.
Okay, yeah. Thank you for pointing that out. I just blew away my denominator of my. Okay, so that's what I need you guys. Keep me honest. Okay, thank you. So for part A here, we've got all we have to remember here is if I've got a to the m over n, that's equivalent to an nth root of a to the m. So I can write these interchangeably. And in order for us to use the power rule, I'm going to want this form. So any radicals, I'm going to immediately put them into exponential form. Okay, so lasso this out of here. I don't have a lot of space. All right, so well, let's try A first of all. So f of x, I'm going to think of it as, instead of 1 over x to the fourth, x to the negative fourth. So f prime of x equals negative 4, x to the negative 4 minus 1 makes that negative 5. So we're done with A. Now B, if we have y equals square root of u, I'm going to rewrite that as u to the 1/2. So if I want y prime, it's going to be 1/2 u. And then if I take 1/2 minus 1, 1/2 minus 1 is negative 1/2. So we could also think of y prime as 1 over 2 times the square root of u. Okay, so I'm just doing two things at once. I'm getting rid of the negative by dropping it down in the denominator, and then I'm changing the rational exponent to a radical square root. So either one of these would be correct. All right, and then lastly, the C option, we're going to take, and I'm going to rewrite this as x to the negative 1/3 power. That's the same thing as 1 over the cubed root of x. Now I can see it in form for the power rule, and I take n, negative 1/3 times x, and then negative 1/3 minus 1. It's going to be negative 4/3. So up here, I'll put negative 4/3. Okay, so that's our last example using power rule here. So we know a constant rule and a power rule, and we're just going to build a few things onto it from that. Here, the constant multiple rule says that if I've got a constant times f of x, or in this case, they've called it u of x because they already said f of x was the combination of these two, then all I have to do is just multiply the result of u prime of x by that constant. So you'll see that this is just a very simple operation. It says if f of x, for instance, equals 3x squared, then I'm just going to take 3 times whatever the derivative of x squared is. So f prime of x doesn't look much like an f. Is going to be 3 times 2x to the 2 minus 1, or 1. So it equals 6x. Part B here, I want to take, I'm going to rewrite this my own way instead of what they're showing. I'm going to say, let's take p cubed over 6 prime. Okay, so that's going to equal 3t squared. Then I have to take that times the 1/6. And I know that 1/6 times 3 is 1/2. So this is going to simplify to t squared over 2. That makes sense? I could have just left the parentheses off and just wrote this as 3t squared over 6 and gotten that. All right, so C. Okay, so for C, y prime is going to equal, let's rewrite that real quick. let's write y in this form instead. We'll take x to the negative fourth over 2. That'll be a little easier to work with. Okay, in that case, then y prime is equal to negative 4x to the negative fifth. And then I have to multiply that by the 1/2, or just divide it by 2. So I get negative 2x to the negative fifth, or negative 2 over x to the fifth. Okay, last one looks like the trickiest here. We're going to say, give me the derivative of 0.4 over square root of x cubed. So again, we want to rewrite that in friendly form for the power rule. So I'm going to make that 0.4 times x, and since it's a denominator, it has to be a negative 1/3, or I'm sorry, 2/3. I'm sorry, 3/2. Okay, so this is x to the 3/2, so that would be negative 3/2. Okay. All right, so my exponent is negative 3/2. I'm just going to take this 0.4 and take the derivative of x to the negative 3/2, which is negative 3/2 x rid of that mess, to the negative 3/2 minus 1. So that's 0.4 negative 3/2. So that's going to be negative 5/2. Now, if I take negative 4 times negative 3/2, I get negative 0.6 x to the negative 5/2. Okay, so just barely had room, but this is our derivative. All right, so that's kind of exhausted all the ways that we can use the power rule together with the constant rule. So now we can see that we can, this is just telling us we can do a derivative term by term. This, all this is saying. So they're just using it in mathematical notation. So they're saying if I've got a function that's built of many terms that are monomial functions, then to get f prime, I'll just take the derivative of each term one at a time. It doesn't matter if it's subtracted or if it's added. Okay, so in that case for A, if f of x equals 3x squared plus 2x, then f prime of x is going to be 3x squared prime plus 2x prime. Okay, so this term, I just take 2 times 3, so 6x to the 2 minus 1. And then this is a 1, right? If I don't put anything up here, it's like x to the first. So I'm going to take the 1 out here times 2. And then this would become x to the 1 minus 1, which is 0. And x to the 0 equals 1. So just, let's go ahead and say, for all time, if f of x equals x, then f prime of x equals 1. Okay, so this just becomes a 1. And So that's A. Let's take a look at B. Okay, if I've got y equals 4 plus 2x cubed minus 3x to the negative 1, then y prime is going to be 4 prime plus 2x cubed prime minus 3x to the negative 1. Okay, so remember, a derivative of a constant 0, so this term is gone. Derivative here is going to be 6x squared and minus, and then the derivative here is going to become negative 3x to the negative 2. I brought this negative 1 out in front and multiplied the negative 3, subtracted 1, but I'm subtracting the result. So when I finally simplify this, don't worry about the 0, and we get 6x squared minus negative, so that's plus 3x to the negative 2. Okay, we're doing quite a lot of these, but I guess, the first go around, that's probably not bad. So I've run out of space, so I'm going to lasso this and clean up and just go ahead and do C and D. Okay, so if I've got y equal, I'm going to rewrite this while I'm at it. So that's w to the 1/3 power, and then minus 3w. And y prime, or here they're asking for dy dw. Same thing as y prime. So it's w to the 1/3 prime minus 3w prime. So that's equal to 1/3 w, and then 1/3 minus 3/3 would be negative 2/3. And then this just becomes the 3 because w prime is 1. So there's our result there. Okay, so if I take the derivative of this entire string, then with respect to x, okay, then I'm just going to go through these one at a time. This is going to become negative 10/3 x to the negative 2 minus 1 makes that negative 3. Now I'm taking a negative 4 times the negative 2 out here, so I'm going to go ahead and bump that into plus 8x to the negative 5th. And here I'm taking plus 3x squared times the 1/9 or over the 9. So all I have to do is reduce this 3 over 9 because this is not reducible. So let's change this 3 over 9 and we'll make it 1/3. Okay, so that's D. Another little tool to learn here is if we've even got enough knowledge to do something like this, even though it looks different than anything we've seen, remember that if you've got a single denominator, you can split and kind of unsimplify it. And so if we write f of x and make it 1 over its denominator of x to the 4th plus x squared over its denominator of x to the 4th, then we can think of it as x to the -4 for this one. And then this would reduce to x. This is like 1 over x squared, so that would reduce to x to the -2. So we can actually calculate f prime of x after we do that to be -4x to the -5th for this guy. And then this would become, since I'm taking a -2 out front, I'll make that minus 2x to the -3. Okay, so given this f of x, the derivative is that. Okay, so now we've got some applications that we can work with since we now know how to more quickly take the derivative. Imagine if we had to run every one of these examples I've done through that difference quotient limit with h going to 0. So we've got shortcuts now. So the instantaneous velocity function is the same thing as the derivative. And that was what we said up top there at the very beginning of class. It was one of the interpretations of the derivative. So let's take f prime of x. Okay, so it's going to equal 3x squared for that first term. Then minus 2 times 6, so minus 12x to the 2 minus 1, which is just 1. And then this is going to just become the constant 9, because I'm going to take 1 times 9 times x to the 0, which is 1. So that's just 9. Okay, so this is our function that calculates for any point x input on the graph of f of x. It calculates the instantaneous rate of change, or the velocity, which is the slope of the tangent line. And b, we're going to find the velocity at x is 2 and x is 5. So we've got our velocity function, so all they're really asking for is f prime of 2. So at 2 seconds, what's the instantaneous velocity? So that's 12 minus 24 plus 9 is negative. And x equals 5. You just have to plug 5 in there. So f prime of 5 is going to equal 3 times 25, so 75, minus 12 times 5, so 60, plus 9, minus 24. Okay, so for C, we want to find the times when the velocity is 0. So we're just going to set f prime of x equal to 0 and solve. So we have, I'm going to factor out 3 here, and it should make this a little easier. So 3 times x squared minus 4x plus 3. When's that equal to 0? The 3 doesn't matter anymore, but I'll keep it there. Okay, so we get a 0 when x is 3. And another 0 when x equals 1. So at both 1 seconds and 3 seconds, velocity is 0. Okay, so it stands still at that momentary point in time. And that's where it changes from a positive to a negative velocity, or vice versa. Let's see. Kind of obscured my next example. This is, I think this is the last one. Yeah, last application. So let me erase this business. Okay, so tangents, it's basically the same thing. It's a repeat performance here. F prime of x, different function, is equal to 4x to the 4 minus 1, so 4x cubed, minus 2 times 6x to the first, so minus 12x. And then remember, it's just plain old 0 or a constant. So that went fast. So we want to find the equation of the tangent line at x equals 1. Okay, so we've seen this before. This is always a little more work than we might think, because this only gives us the slope of the line at x equals 1. So let's get the slope of x equals 1. Okay, so m equals -8, but I also need a point on the line. And that's just f of 1. So going back to f of x, I'm going to take 1 minus 6 plus 10. Okay, so it's 5. So now we know that the point on f is at x equals 1 and y equals 5. That's where my tangent line is -8. So we've got all the parts we need to build our line. Not room to do it, but okay, so remember y minus y1 or 5 is equal to slope -8 times x minus x1, which is 1. Okay, so we usually like to give the lines in function form. So we're going to write this as y minus 5 equals -8x plus 8. And then adding our 5 to both sides, we get y equals -8x plus 13. Okay, so if we graphed this line together with this function, this is the line that's going to touch this graph at a tangent point through x equals 1, y equals 5. Okay, now a horizontal tangent means m equals 0. So for part C, we're doing the same thing, setting it equal to 0 and solving. So when this is essentially asking, so I'm gonna clean up some space here and we'll get C done. Actually, I still want A, so let's just get rid of B. Okay, so when is the tangent line horizontal? That means when is the tangent calculator f prime of x equal to 0. So now setting this equal to 0 and finding the values of x, we've got our answer. So when is 4x cubed minus 12x equals 0? And again, we got a factor at work here of 4x. So this becomes x squared minus 3. Okay, so when is x squared minus 3 equals 0? Add 3. Well, that happens when x squared equals 3. or x is equal to plus and minus a square root of 3. Okay, so that's when we're going to have, for this graph of f of x, if we put that into GeoGebra, like I like to do in class sometimes, and we ask for the tangents at positive and negative square roots of 3, we're going to get horizontal lines for the tangents, both places. Okay, so that's a rundown with a couple of applications and just your new tools, your kind of shortcuts to that lengthy process of finding the limit here. So you probably won't see this again for a little while since we got all these shortcuts. All right, so I'm going to close off the video, and if you guys have any questions, just stick around and ask them.